Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we're going to discuss multiplication and factoring of whole numbers. I'm reminded of the story of the little boy in the 3rd grade who was asked to write a composition, and the composition had to be 200 words long. And the youngster was terrified of having to think of 200 words, and finally he solved this problem. He wrote, "We have a cat, my cat got lost. I went outside and I said, 'Here, kitty, 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 kitty.'" That may sound like a silly story, but sometimes we have to do addition that way. Suppose you're going out and you're buying 15 pencils at 7 cents each. Technically speaking, if you wanted to add up how much the pencils were going to cost you, you'd have to say 7 plus 7 plus 7 plus 7 plus 7 plus 7 15 times. And what we'd like to do is to get a more compact, shorter, and more intuitive way of being able to do that. And to get back to our central theme about numbers being adjectives modifying nouns, when you count 1, 2, 3, 4, 5, etc., you really mean 1 what, 2 what, 3 what, 4 what, 5 what. See, the whole numbers are adjectives modifying nouns. So suppose you were buying pencils at 7 cents each. If you were buying 3 pencils, you might be interested in counting the number of pencils. You'd say 1 pencil, 2 pencils, 3 pencils. But if you were interested in the cost at 7 cents each, you might say 1 7 cents, 2 7 cents, 3 7 cents. And you would then be counting by sevens, and this is what we mean by the multiples of sevens, and that's the word multiple leads to the idea of multiplication. And so with that as an introduction, let's go over to the board and begin our present discussion. What I'd like to start with today is the story of the 3 pencils at 7 cents each. Rather than count the pencils, let's count how much the pencils cost. And what we'll do is we'll use a tally mark to represent each cent. So the first pencil costs 7 cents. That's 7 tally marks, 7 more tally marks for the second pencil, 7 more tally marks for the third pencil, and we could actually count the number of tally marks. But the shorter way is to notice that you have 7 tally marks, then 7 and 7 more is 14. You see we're doing addition here, and 14 plus 7 is 21. You see 1 7 is 7, 2 7s are 14, 3 7s are 21. And we invent a shortcut notation for writing that. What we do is we write 7, and this x is read times, 7 times 3, and what's that an abbreviation for? The first number, in this case the 7, tells you what number you're going to be adding. And the second number tells you how many terms are going to appear. See, this really means the sum of 3 sevens. And that may seem awkward. You see how I'm reading this? I'm not reading it as 7 threes. I'm saying the sum of 3 sevens. And in a little while, I'll explain to you 2 things. One is why we write it this way, and the other is why it doesn't really matter, except for philosophical reasons. But 7 times 3 is an abbreviation for 7 plus 7 plus 7, and that's the same as 21. And when we write that, the 2 numbers here, what we mean what? The third multiple of 7? The 7 and the 3 are called the factors. And the answer to the problem, in this case 21, is called the product, okay? Factors and product. And the language that we use is that when we write 7 times 3, what we mean is what is the third number you'd come to if you counted by sevens. In other words, 7 times 3 means the third multiple of 7, and it means if you were counting by sevens, see 7, 14, 21, what's the third number you'd come to? You see, 3 times 7 would mean the 7th multiple of 3. And that would mean if you were counting by threes, what's the 7th number you'd come to? See, 3, 6, 9, 12, 15, 18, 21. Lo and behold, the same answer. And yet, surprisingly enough, see, when you say the 7th multiple of 3, you mean 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3. When you say 7 times 3, that's the third multiple of 7, you mean 7 plus 7 plus 7. Now notice that these 2 don't look alike. You see what I'm saying here? Here you can see the 3, but the 7 is implicit. You have to count the number of 3s. Here you can see the 7, but the 3 is implicit. You have to count the number of 7. See, 1, 2, 3. Why should the sum of 7 3s be the same as the sum of 3 7s? And the easiest way to see that is to come back to the beginning of the lecture and look at a new way of counting the tally marks. You see, when I counted these tally marks, I counted them as what? 7 in a row, and I had what? 3 rows of 7. I could have added by the columns. See, each column would have 3. And how many columns do I have? 7. You see, I could either say I have 3 rows of 7, or I have 7 columns of 3. In other words, the third multiple of 7 should be the same as the 7th multiple of 3. And that's called, just as an addition, the commutative property. And the commutative property is very important. In the same way that 39 plus 3 was psychologically easier to solve, say, than 3 plus 39, it's much easier to find the second multiple of 75 than to find the 75th multiple of 2. You see what I mean here? See, suppose I say to you, what is the 75th multiple of 2? Well, if you count by 2s, first of all, how would this notation read? You're adding up the 2s. How many terms are there? How many 2s? 75. See, what this says is if you were counting by 2s, what's the 75th number you'd come to? Well, this is a hard problem. See, 2, 4, 6, 8, I'm only at the 4th one. But notice that the sum of 75 2s is the same as the sum of 2 75s. In other words, imagine 2 rows underneath each other in a rectangular form, each with 75 tally marks. I either have 2 rows of 75, or I have 75 columns, each with 2. But the easy part is that the second multiple of 75 is 75 plus 75, which is 150. In other words, if I count by 75s, 150 is the second number I come to. So the amazing thing is that without doing the problem, I can now say that if I were counting by 2s, 150 would be the 75th number I'd come to. Now the interesting thing is, in the same way that I made the addition tables by only knowing how to add 2 single digits at a time, I can do the same thing with multiplication. For example, if somebody says to me, how much is 9 times 4? What they're saying to me is, find the 4th multiple of 9. That means if you're counting by 9s, what's the 4th number you come to? You see, and that's just an addition problem. 9 and 9 are 18, and 9 more is 27, and 9 more is 36. So 9 times 4 is 36. That also means, of course, that 4 times 9 is 36. Now, in doing this, did you notice what I said? See, the first multiple of 9 is 9. The second multiple of 9 is 9 plus 9, which is 18. The third multiple of 9 is just going to add 9 more onto this. And before you know it, I can construct the 9 table this way. And I can construct all the tables this way. See, if I wanted to find out how much 8 times 6 was, I could write down what? The sum of 6 eighths. And that would turn out to be 48. There are 2 very special products that we should be interested in. One of them involves the number 1, and the other involves the number 0. You see, 7 times 1 means the first multiple of 7. In other words, if you're counting by 7s, what's the first number you come to? Well, heck, 7. In fact, if you're counting by n's, where n is any whole number, the first number you come to is n. In other words, any number times 1 is still that number. And the other magic number is 0. See, what would 0 times 3 mean? It would mean the third multiple of 0. That means if you were counting by zeros, what's the third number you'd come to? Well, you see, 0 plus 0 plus 0 is still 0. So the product of any number and 0 is still 0. That should not be confused with the sum of any number and 0. See, when you add up a whole bunch of zeros, you still have zeros. But when you add 0 to a number, you still have that number. See, 0 plus 3, for example, is 3. Okay, do you follow that basic idea? Now, here's the problem. It's relatively easy to say, what's the 8th multiple of 6? What's the 4th multiple of 7? In theory, if I said to you, what was the 21st multiple of 43? In theory, that's exactly the same as the problems we've just done. But do you notice that the arithmetic seems a little bit more difficult now? See, let's look at that in more detail. If I say to you, what is the 21st multiple of 43? How would we write that? The number you're adding is 43. How many 43s are you adding? 21. See, this is written as 43 times 21. It's called the 21st multiple of 43. And what it means is, if you were counting by 43s, what would be the 21st number you'd come to? At which point you could say to me, what person in his right mind would even want to do that kind of a problem? Well, for example, suppose you were buying cat food at 43 cents a can, and you were buying 21 cans. See, the first can would cost you 43 cents, the next can would cost you 43 cents. So if you're counting by cost rather than by cans, you're counting 43 cents once, 43 cents twice, 43 cents 3 times, etc. And what you want to do is what? Writing it vertically here, you want to add up what? 21 43s. And by the way, even though you can do these 2 at a time, it's a pretty messy problem. See, you could say what? 43 and 43 is 86. And 1 more 43 is 129. So if I buy 1, 2, 3 cans of cat food, it costs me $1.29, and I only have 18 more 43s to add on so far. Or you could make a key observation and shorten this problem enormously. The key point is that the sum of 10 43s is 430. To add up 10 of any amount, all you have to do is annex a 0 after the number. And let me show you why that's the case. See, when I write 43, 3 is an adjective modifying 1s, 4 is an adjective modifying 10s. Suppose I put a 0 after the 3. What is that 0 doing? It's holding the place of the 1s column. See, the 0 is now in the 1s place. That means the 1s have now become the 10s, and the 10s have now become the hundreds. You see, I've traded in 10 1s for a 10 and 10 10s for 100. And by the way, if you think this is a miracle, the same thing happens with Roman numerals. See, in Roman numerals, 43 would be 4 x's and 3 i's. How would you write 10 43s? All you would do is convert each x to the next highest denomination and each tally mark to the next highest denomination. See, the i's become x's, the x becomes c's, so 43 becomes what? 4 hundreds and 3 10s, that's 430. And by the way, if you don't believe this, just figure it out for yourself, as I may have said in the previous lecture. See, 2 times 10 is 20, because if you add up 10 2s, see what happens? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. The final answer is your 2 followed by a 0. So with that in mind, you see, every time I add up 10 43s, that's 430. 10 more 43s would also be 430. And 1 more 43 would be 43. So altogether, what do I have here? 10 43s, 10 more 43s, 1 more 43. There's my 21 43s. And now what does this add up to? 903. In other words, if I were counting by 43s, the 21st number I would come to is 903. And if you don't believe that, you could check it out. And in terms of the cat food problem, at 43 cents each, 21 cans of cat food would cost $9.03. Now, we don't usually do the problem this way. Most of you, I'm sure, have been taught multiplication before, and I'd like to revisit the way that you've been taught most likely. Let's take a look over here. First of all, when you say 43 times 21, notice that you usually write it in vertical form. The first number goes on top, the second number goes on the bottom. In other words, notice that you're taking 43 21 times here. Now, at any rate, let's do this problem mechanically. Do you remember how you were taught to do this? We've assumed now that you've learned the multiplication tables for single digits. 1 times 3 is 3, 1 times 4 is 4, 2 times 3 is 6, 2 times 4 is 8. But notice that when we wrote the 6 over here, we put it under the 4, not under the 3. And the question is, why did we do that? And the answer is that although this looked like a 2, as an adjective it was a 2, but it was modifying 2 10s. 2 43s is 86, but 20 43s is not 86. It's 860. You see, the point is, by putting the 6 under the 4, where is the 4 right now? The 4 is in the tens place. So by putting the 6 here, it was the same as if you had written 860. And this is a very important point. You see, what you're really saying is that 1 43 is 43, and that 20 43s is 860. So if you add up 1 43 and 20 more 43s, altogether you have 21 43s, which is 903. And by the way, how long did it take me to write in the symbols in red here? Maybe 10 seconds. That 10 seconds is the difference between your going through life understanding multiplication and going through life memorizing it. All I want you to see that this procedure over here was the same thing we did before. Remember, 1043s was 430. 430 and 430 is 860. There's your 860. There's your 43. In other words, what we observed is that if you want to find out how much 21 43s are, all you have to do is write 21 as 20 plus 1. Then you have what? 20 43s and one more 43. This is called the distributive property. You see, I have two numbers being added, and I'm multiplying the sum. You see, for the first time, I have addition and multiplication in the same problem. We talk about that more in the text. But just for the time being, let me just mention the name. It's called the distributive property. And what it says is, when a number multiplies the sum of two or more numbers, the number must multiply each of the numbers in the sum. Let me show you an intuitive way to see this. Suppose I add 3 and 4 and then multiply that by 2. In terms of tally marks, 3 plus 4 would look like this, wouldn't it? So 3 plus 4 2 times would be this thing written twice. And if I now look at the way I've written this, notice that I've written 3 twice and 4 twice. So in other words, if I double 3 plus 4, it's the same as doubling 3 and doubling 4. You see what I'm saying here? This is 6, this is 8. 8 plus 6 is 14. But if I added 3 and 4, that would give me 7, and 2 times 7 would also be 14. So basically, that's the structure of addition. And I'm going to show you this in even more dramatic fashion right now. I'm going to show you something which I think is very, very exciting, and something that's going to make multiplication, I believe, a very easy subject for you if you'll do it my way. Let's make what I call a noteworthy observation. Last time we saw that when you learned that 2 plus 1 is 3, that was the same as learning that what? 2 tens plus 1 10 is 3 tens. Suppose you knew that 2 times 1 is 2. What would 2 tens times 1 10 be? Well, 2 times 1 is 2. What's the label over here? You're going to say tens, aren't you? Be careful. It's 2 hundredths. You see, 2 tens is 20, isn't it? And 1 10 is 10. And if you count by 20s, the 10th multiple you're going to come to is what? 200. See, 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. You see, the amazing thing is that when you multiply, you don't keep the common denomination or the non-common denomination. You actually combine the denominations. You see, what you really say is what? 2 times 1 is 2. 10 times 10 is 100. It's a very amazing fact. Let me give you another example. Suppose I say to you, how much is 200 times 3,000? You see, the idea is 2 times 3 is 6. That's the adjective multiplication. What are the nouns? Hundreds and thousands. How do you multiply hundreds by thousands? Just put the two words together. See, 200 times 3,000 is 600,000. A rather amazing thing. And by the way, some of you may have been taught this a different way. See, 200 times 3,000. The way I was taught this in school was you multiplied the 2 times the 3, that was 6. Then you counted the number of zeros, 1, 2, 3, 4, 5. Then you put the comma in. What answer did I get that way? 600,000. But the difference is I can see what's happening over here, and this is sort of just a memorized device. By the way, you do this all the time in multiplication problems. Suppose I were to say to you that a person drove at an average speed of 50 miles per hour for 2 hours. And I say, how far did the person go? You say, that's easy, it was 100 miles. I say, how'd you get that? You say, well, I just multiplied 50 by 2. No, the 50 and the 2 are just adjectives. What you multiplied was what? 50 miles per hour times 2 hours. Aren't these different labels? You see, the 50 times 2 gave you the 100. But miles per hour times hours gave you miles. You see, you need common denominations for when you're adding, but you don't need them for when you're multiplying. But once you know this, let me revisit the multiplication problem and show you another way of doing it. See, let me show you another way to look at 43 times 21. When you multiply 1 times 3, the answer is 3, isn't it? But what are the nouns? Ones and ones. 1 times 1 is 1, so the 3 goes in the ones place. 1 times 4 is 10. What are the nouns here? Ones and tens. 1 times 10 is 10, so the 2 goes in the tens place. When you said 2 times 3 is 6, 6 what? Tens times ones is 10, so the 6 goes in the tens place. 2 times 4 is 8, but 8 what? Tens times tens, that's 800s, so the hundreds go, the 8 goes in the hundreds place. You notice that you never had to multiply more than 2 digits at a time. Now you add up, you have what? 3 ones, 10 tens, and 8 hundreds. Now you can take your 10 tens and trade them in for what? 1 more 9, and there's your answer, 903 again. And if you remember this, this will help you guard against some very, I call them gross errors, okay? What about the kid who says, okay, 1 times 3 is 3, 1 times 4 is 4, 2 times 3 is 6, 2 times 4 is 8, writes the 86 under the 43 and says, that's how you do it my way. Well, look at this problem. As soon as you put the 6 under the 3, you were saying 6 ones, weren't you? In other words, if you did the problem this way, no matter how you write this, you were really reading this as saying what? 143 is 43, 2 more 43s are 86, so altogether you have 129. You see, it's imperative that the 6 go over here, because to get the 6, it's what? 2 tens times 3 ones, tens times ones are tens. Let's do this, a similar problem, but only with some bigger numbers here, just to emphasize this. Suppose I said to you, what is the 34th multiple of 57? So that's what? 57 times 34. See, now you're buying 34 cans of dog food at 57 cents each. Watch how this new method works. You say something like, let's see, 4 times 7 is 28. Where do we put the 28? Ones times ones are ones, so the 28 goes in the ones place. 4 times 5 is 20. 20 what? Ones times tens are tens, so the 20 goes in the tens place. 3 times 7 is 21. 21 what? Tens times ones. See, tens times ones, so the 21 goes in the tens place. 3 times 5 is 15. 15 what? Tens times tens is 100, so 15 goes in the hundreds place. Now you add up. You have 28 ones, 41 tens, and 15 hundreds. If you want, you can take 20 ones and trade them in for 2 more tens. See, you only have 8 ones, but 2 more tens. Then you can take 40 tens and trade those in for 4 more hundreds. So now the answer would be what? 1,938. In other words, if you had taken the time to actually count by 57s, if I haven't made a mistake here, the 34th number you would have come to is 1,938. And notice how you never have to multiply more than 2 digits at a time this way. You never have to carry until the problem is all done. But still, we like to teach a faster way. This is explained in the textbook. The way we usually do it is we say what? 4 times 8 is 28 ones. We'll put down the 8 and carry 2 tens. See, 4 times 5 is 20, and 2 is 22. 3 times 7 is 21. Put down the 1 and carry the 2. 3 times 5 is 15, plus the 2 that you carried is 17. And so what this method does is it does exactly the same thing that we did over here, only now you have to keep track of carrying at the same time that you're multiplying the digits. I would do it the first way, the way I just showed you, first until you have a feeling for that. Then when you feel comfortable, shift over to the faster way. Always go 1 step at a time. It's a real neat way. And this works no matter how many digits you have. Let's see, let me show you another problem. How much is 723 times 134? This says if you were counting by 723s, what's the 134th number you'd come to? There's your kitty story all over again. Look at all the 723s you'd have to add up. But see, the way we do this is we say what? 4 times 3 is 12, put down the 2 and carry the 1. 4 times 2 is 8 and 1 is 9. 4 times 7 is 28. 3 times 3 is 9. 3 times 2 is 6. 3 times 7 is 21. See how we're indenting to keep track of the denominations? 1 times 3 is 3. 1 times 2 is 2. 1 times 7 is 7. And now we add these all up, and we get 96,882. And to have you see what's happening over here, let's put the zeros back in. See, this is how much 4 723s are. This is how much 30 1/34 are. And you see, because the 1 is in the hundredths place, this is 723/100. You see, by putting the 3 under the 8, the 3 is already in the hundredths place. You see, what's happening is this number plus this number plus this number is what? 4 plus 30 plus 100, or 134 723s. And if you understand this, this is still going to help you prevent making big mistakes. Let me show you a similar problem, but one which people very often make mistakes on. Let's now look at how much is 231 times 102. See, what's the 102nd multiple of 231? If you're counting by 231s, what's the 102nd number you come to? Well, the correct way of doing this is if we do it mechanically, we say 2 times 1 is 2, 2 times 3 is 6, 2 times 2 is 4. Then we say 0 times 1 is 0, and we indent. 0 times 3 is 0. 0 times 2 is 0. It looks like a kind of babyish way putting in all these zeros. I'll explain that in a minute. Then we indent again. 1 times 1 is 1. 1 times 3 is 3. 1 times 2 is 2. Then we add these all up. Now, the reason we indented this way was the following. By putting the 1 over here, that put it in the hundredths place. Notice that the 1 over here is an adjective, but it's modifying hundreds. This is 100 231s, and 100 231s is 23,100. In other words, this was 2 231s, and this was 100 231s. I've just summarized that below, and we won't go into that right now. But basically, what you've really done here is you've added up what? 102 231s. You see, if you get sloppy on this problem, what you might be inclined to do is to say this. 2 times 1 is 2, 2 times 3 is 6, 2 times 2 is 4, so you write down the 462. Then you say, well, what the heck, 0 is nothing, I'll just skip it. So 1 times 1 is 1, 1 times 3 is 3, 1 times 2 is 2. You add this up, you get 2,772. You say, well, my answer is different than yours, but it was quicker. But let's see what the right answer means. You see, as soon as you put the 1 over here, under the 6, you were putting this in where? The tens place. In other words, whether you realize it or not, this is not 100 231s, this is 10 231s. See, when you wrote the thing this way, it was like we were talking about before, what you've really found out over here is how much is 12. How much is 12 231s? That 0 here was not holding a place of anything, because by not indenting enough places, you treated this as a 10 rather than as 100. By the way, I taught you how to estimate when we did addition. Do the same thing again. Whatever 231 times 102 is, look, isn't 231 bigger than 200? And isn't 102 bigger than 100? Therefore, whatever 231 times 102 is, it must be bigger than 200 times 100. But what's the fast way to multiply 200 by 100? 2 times 1 is 2. 1 0, 2 zeros, 3 zeros, 4 zeros. 200 times 100 is 20,000. Therefore, 231 times 102 has to be bigger than 20,000. Consequently, this answer is at least plausible. This answer is completely implausible. If the right answer has to be bigger than 20,000, no matter what the right answer is, we know it can't be 2,772. But just in summarizing this, what I want you to see over here is that when you take 102 231s, 100 231s just means you take 231 and tack on 2 zeros. 2 more 231s is 462. So there is an addition way, rapid repeated addition, to help you visualize why 231 times 102 is 23,562. Now, we're going to do more drill on multiplication, as this is called, both in the study guide and in the textbook. And I will come back in the next lecture, of course, to go through the exercises on this. But now I want to show you that in the same way that the invention of addition forced us to invent subtraction, the concept of multiplication forces us to invent something called factorization or division. And again, notice how important it is to listen carefully. Suppose I asked you this problem. What must we multiply by 4 to get 8 as the product? The most common wrong answer here is 32. And why do people say 32? They read too fast. They see the word multiply, they see the numbers 4 and 8. They know that the fourth multiple of 8, 8 times 4, is 32. But read this problem carefully. It says, what must we multiply by 4 to get 8 as the product? See, 8 is the answer here, not one of the factors. This says what? 4 times blank equals 8. See, the answer is not 32. The answer is 2. And the way we write this is to indicate when we had 4 plus blank equals 8, we said blank equals 8 minus 4. When we have 4 times blank equals 8, we say blank equals 8 divided by 4. This is called a division sign. And 8 divided by 4 is just another name for what number must you multiply by 4 to get 8 as the answer. See, and the reason we call it divide is that if you take 8 and divide it into 2 equal parts, see, each part has 4. Or if you take 8 and divide it into 4 equal parts, each part has 2. But there's a new vocabulary associated with this. The answer to a division problem is called the quotient. The number to the left of the division sign is called the dividend. The number to the right is called the divisor. Most kids like to write these as what we call gazinta problems. See, that they write 4 gazinta 8 2 times. Basically, what's tricky here is with the division sign, the 8 comes first and then the 4. But when you write it in what we call the division form, the 4 is the outside number and the 8 is the inside number. You see what happens now? The divisor has come over here. This is the dividend and this is the quotient. Now, it was easy to fill in the blank when you said 4 times blank equals 8. Let's take the same kind of theory but ask a more complicated computational question, even though the theory is equivalent. See, now what we're going to ask is, fill in the blank. 13 times what equals 2,821? What this is saying is 2,821 a multiple of 13? And if so, what multiple is it? In still other words, if you were counting by 13s, would you eventually come to 2,821 exactly? And if so, what number in the list would that be? Can you visualize how complicated the problem that is? Let's try to do it by trial and error. You say 13 times 1 is 13, 2 13s is 26. See what we're doing? We're going to add on 13 each time. 13 times 3 is 39. Since 39 and 13 is 52, 13 times 4 is 52. 13 times 5 is 65. See what we're doing? We're counting by 13s. The sum of 6 13s is 78. 1 more 13 gives me 91. 1 more 13 gives me 104. 1 more 13 gives me 117. By the way, you don't have to do it this way. I'm just trying to show you what it means to take multiples. You could say what? The ninth multiple of 13 is 13 times 9. 9 times 3 is 27. Put down the 7 and carry the 2. 9 times 1 is 9, and 2 is 11. There's your same 117, the fast way. But as you're doing this, you say, oh my golly, I've added up 9 13s, and I'm only at 117 so far. I got quite a ways to go before I get to 2,821. Well, let's go back to our idea that when you count by bundles of 10s, you just annex a 0. Since 100 is 10 times 10, to multiply by 100, you tack on 2 zeros. Now watch what starts to happen over here. See, since the second multiple of 13, see, since 13 times 2 is 26, 13 times 200 will be 2600, which we write this way. See, 13 times 3 is 39, so 39 times 300 is 3900, which we write like this. By the way, some people will say to me, how do you know whether you read this as 3900 or 3900? The answer is simple. You see, since the 9 is in the hundreds place, if I read this in terms of hundreds, I have what? 39 hundreds. If I want to read by thousands, I have 3 thousands and 9 more hundreds. See, 3,900 is just another way of saying 3,900. But now let's go back to this problem, which we'll finish as part of problem number 11 later in this lecture. But the thing I wanted to show you now is that if you added up 200 13s, you'd have 2,600, which is less than the 2,821 that we want. And if you added up 300 13s, you'd get 3,900, which is too big. So going back to the problem again, if you look at the fill in the blank, whatever the right number is to put in over here, 200 would be too small and 300 would be too big. And I'm going to show you in a few minutes how we find the exact answer. But let's just continue on this way. Let's make sure you understand the new vocabulary. See, is 83 a multiple of 13? What that means is, if you were counting by 13s, would you eventually ever get to 83? Well, see, when you're counting by 13s, and you can review this if you want, I don't want to start counting all over again. When you're counting by 13s, we just saw that the sixth number you came to was 78. And the seventh number you came to was 91. See, with 13 as the noun, you have more than 6 13s, but less than 7 13s, and there are no whole numbers between 6 and 7, so 83 is not a multiple of 13. In other words, when you're counting by 13s, you go from what? A number below 83 to a number above 83. You follow the idea here again? And in case I am going too fast, if this bothers you, 13 times 6 is what? 6 times 3 is 18. Put down the 8, carry the 1. 6 times 1 is 6, and 1 is 7. So you can get these things if you want them. Now, let's reword this problem. If I can put 13 books into each carton, how many cartons will it take to pack 83 books? See, I've got 83 books. I can put 13 books in the carton. How many cartons is it going to take? Well, to recapitulate this problem, I just saw that if there are 13 books in the carton, 6 cartons would be 13 books 6 times. We just saw that that's 78 books. So if I were to subtract 78 from 83, giving me 5 as a remainder, see, whatever is left over when it's not a multiple is called the remainder. What this tells me is what? At 13 books per carton, 83 books will give me 6 complete cartons plus 5 left over. Well, since I want to put the 5 left over into a carton, I need what? 7 cartons. 6 full ones, and the 7th one has what? 5 of the 13 parts that I need to fill up the next carton. And by the way, that language is going to lead to fractions later on. See, I have what? 6 full cartons and a fractional part of another. What fractional part? 5 out of the 13 that I need. That will come back to be a big issue later on. But for the time being, let's see how we write this as a Gazinta problem. See, we say 13 goes into 83. We say, let's see, 13 doesn't go into 8, because 8's too small. 83 is bigger than 13. How many 13s are there in 83? 6, because 7 would be too big. We put the 6 over the 3. 6 times 13 is 78. We put the 78 under the 83. Then we subtract, and we write the answer as what? 6 with a remainder of 5. Now, let's come back to the problem as to whether 2,821 is a multiple of 13. In other words, is there a whole number that I can put in here that will make this a true statement? And let's go back to the 13 books per carton problem again. See, what I can say is, every time I pack 13 books, I'm going to fill up one more carton. So after the first carton is filled up, I subtract 13 from 2,821. That tells me I still have 2,808 books to put away. I now pack another carton. That gets rid of 13 more books. I subtract 13 from 2,808, and I have 2,795 books to put away. In other words, at this stage of the game, look what's happened. I have filled up 2 cartons, and I still have what? 2,795 books to put away. You see that kitty story coming back again? Look how long this is going to take me. But I become shrewd here. Watch what I do now. Go back to what we said before. 1 carton holds 13 books. So 10 cartons will hold what? 130 books. See, to multiply by 10, you tack on a 0. 100 cartons will hold 1,300 books. By the way, if 100 cartons holds 1,300 books, 200 cartons will hold 1,300 books. 2 13s are 26. 2 times 1,300 is 2,600. Do you follow the idea over here? Okay? Now watch this. Since there are 13 books in the carton, 200 cartons have what? 2,600 books in them. Look at this human computer working here. As soon as I subtract 2,600 from 2,821, I have in effect packed 200 cartons. In other words, if I hadn't made a mistake the other way, by the time I subtracted 13 for the 200th time, if I didn't make a mistake, I'd have gotten down to here. See, in one subtraction, I can now say, look it, after 200 cartons are filled up, I still have 221 books to put away. Can I take out any packages of 10 13s, from 221? Sure, 10 13s is 130. 20 13s would be 260, that's too much. I can take out 10 more cartons. 10 cartons holds 130 books. So after those 10 cartons are filled, I still have what? 91 books left. And how many cartons of 13 can I fill from 91? Well, since I already saw that 13 times 7, I'll just review that for you. 1 carries a 2. Since 13 times 7 is 91, I can fill up 7 more cartons, then I have no books left, do I? You see how fast this was? In effect, how many cartons did I fill here? 217. And by the way, I should check this for you later. If I've done this correctly, 217 multiplied by 13 should give me 2,821. I will do that check after we do it in what I call the long division format, the Gazinter way. See, the way we solve this problem is we say, let's see how many times 13 goes into 2,821. So 13 doesn't go into 2. 13 goes into 28 2 times, so we put the 2 over here. Then we say 2 times 13 is 26. Then we subtract, okay? We subtract. That gives us a 2. Now I bring down the next digit, that's a 2. 13 goes into 22 how many times? 1 times 13 is 13. 2 times 13 is 26. So 2 would be too much, so I put a 1 over here. 1 times 13 is 13. 13 from 22 is 9. See how I'm using subtraction? Now I bring down the 1. 13 goes into 91 7 times. 7 times 13 is 91. Do most of you remember this method? This looks quicker than this, but this, I think, looks more informative, doesn't it? And what I want to show you is that these two methods are identically alike. Watch. I'm going to switch back between this and this, and just watch what I'm doing here. When you put the 2 over here, that was over the 8, wasn't it? And the 8 stands for the hundreds. This wasn't a 2, this was really 200. And 213's on 26. It's 2600, you see. And when I subtract 2600 from 2,821, I have 221 left. This looks like a 1, but since it's over the 2, it's 110, which is 130. 130 from 221 is 91. And what I wanted you to see was, if I circle this, and I circle this, look at the two things that are circled, if you can see them okay, and notice that they're exactly the same. Exactly the same. By the way, should you want to check this, see 217 times 13, just multiply this out and you get 2,821. By the way, you could also have changed the order here. You could have put the 217 on the bottom and the 13 on top. See, 7 times 3 is 21, carry the 2. 7 times 1 is 7 and 2 is 9. 1 times 3 is 3. 1 times 1 is 1. 2 times 3 is 6. 2 times 1 is 2. And now what you'll notice is, if you add these up, there's your 2600, your 130, and your 90. Look how all this stuff just ties in together. And by the way, when you're doing long division, just a few precautions. First of all, suppose you took a guess that was too big. You say 13 goes into 28 3 times. The safeguard will be 13 times 3 is 39, and how do you know you've made a mistake? You're taking away more than what you have. You can't do that. Suppose you took too small a guess. Suppose you said 13 goes into 28 once. Then you would subtract 13 from 28 and you'd get 15. The clue that you've done something wrong is that if you don't bring a number down, the remainder always has to be smaller than the divisor. Because what this says is what? Since 15 is bigger than 13, can't I take out one more bundle of 13 from here? See what I'm saying? In other words, if you should make a mistake, just adjust it. Take out one more bundle, or 2 more bundles if you can. The third thing you have to be very careful about is every time you bring a digit down from the dividend, something has to go up into the quotient. For example, in this problem, if you say 13 goes into 27 twice, 2 times 13 is 26, so now you subtract. Now you bring down the 1. You see, the problem is that 13 doesn't go into 11. What you have to do is, since you brought the 1 down, something has to go up here. So you bring a 0 here, then you bring down the 7. Then you say 13 goes into 117 9 times. 13 times 9 is 117. Bring the 9 up here. So the answer is 209. And to check this, if you actually took 209, multiplied that by 13, that would give you the correct answer. I leave the details for you here to check. But the thing I want you to be very, very careful about, if you leave this 0 out, you've got the wrong answer. Because if you leave this 0 out, the 9 coming over here puts the 2 in the tens place, and 13 times 29, you see, 13 times 29 is nowhere near 2,717. See, 13 is less than 20, 29 is less than 30, 20 times 30 is only 600. That's way less than 2,717. See, what I want you to see here is that when you put the 2 over here, this was still 2,600. When you subtract 2,600 from 2,717, you have 117 left. To take out a bundle of 10 13s, you would need 130. You only have 117, so you can't take out any bundles of 10. You see, you need the placeholder here. And basically, that's all I want to say about the mechanics of this. But to show you why this is so important, of all the 4 basic operations of arithmetic, addition, subtraction, multiplication, and division, even though I did division last, it's the single most important operation. Division may be the single most important operation in all of mathematics. And the reason is that in the real world, we don't know how to measure things absolutely. We can only measure them relatively. For example, if I gave you a choice between being either good, better, or best, which would you choose? You say, I want to be best. But couldn't you have 3 awful things, none of which are good, but one of which is the best of the 3? See, good is an absolute term, best is a relative term. So if you say to a person, 6 divided by 2 is 3, this says something very significant. Suppose I say to you, is 6 a great number or a small number? What this says is, I don't know, but compared to 2, it's 3 times as big. Do you ever drive in your car and look ahead of you and see the bumper sticker on the car ahead? It says, I may be slow, but I'm still ahead of you. See, 6 may be small, but it's still 3 times as big as 2. Why are we interested in this? Well, the answer is that whenever you want to measure a relative size, that's called a rate. It's a division problem. Let me just go through something very rapidly with you. When I say how much is 6 miles plus 2 miles, the answer is 8 miles. If I say how much is 6 hours plus 2 hours, the answer is 8 hours. If I say how much is 6 miles plus 2 hours, that doesn't make sense because there's no possible common denomination that ties in miles and hours. But if I say to you, how much is 6 miles divided by 2 hours, 6 divided by 2 is 3, and miles divided by hours is called miles per hour. In fact, that's where fractions are going to come from. Namely, when you divide the number of miles by the number of hours, the answer might not be a whole number. I mean, if you went 6 miles in 5 hours, you've gone more than 1 mile an hour, but less than 2 miles per hour. But without worrying about that, you see, when you put the word per between 2 nouns, that's called a ratio or a rate. A rate is always 2 nouns separated by the word per, miles per hour, dollars per pound, and rate is sometimes very important. For example, if you're driving on the highway and all of a sudden you see the flashing lights of a state trooper behind you, what do you do at that point? Do your eyes drop to a road map, or do they drop to the speedometer? You see, at that particular time, you don't care how far you've gone, you care about how fast have I gone, and that's a rate problem. Let me show you what I mean by that. Suppose 3 different people drive 60 miles. That doesn't tell me anything about their rate. See, if the first person took 2 hours, 60 divided by 2 is 30, and that's called what? Miles per hour. See, miles per hour is miles divided by hours. It's not one word. When I was a little kid, I thought neck and ears was one word, because my mother would say to me, go wash your neck and ears. Most people hear miles per hour, and they hear it as one word. Hear it as 3 words. It's miles divided by hours. You see, suppose another person went 60 miles, but it took him 3 hours. 60 divided by 3 is 20. That means he is going at a rate that only takes him 20 miles every hour. Suppose another person traveled 60 miles, but it took him 30 hours. Now 60 divided by 30 is 2. His rate is 2 miles per hour. You see, all 3 of these people went the same distance, but their rates were substantially different. The word rate has the same stem as the word ratio. Ratio has the same stem as the word rational. rational numbers are what we usually call fractions, and that will become the subject matter of the next 5 lectures. But meanwhile, our next meeting will be when we go through exercise set 3, Form B. Until then, continue to study hard, have fun, and I look forward to seeing you all again for the next meeting. Bye now.